Bismillahirrahmanirrahim. Hello students, welcome to the electrical engineering channel. Now I will discuss the cylindrical coordinate system. So actually we have three types of coordinate systems. The first type is called Cartesian coordinate system, or it is also called rectangular coordinate system. Second coordinate system is cylindrical coordinate system, and the third is the spherical coordinate system. Spherical coordinate system will also be discussed in the coming lectures. And in cylindrical coordinate system, we can represent any point or any vector using three components. So in cylindrical coordinate system, we have three components: rho, phi, and z. Rho is the radially outward going vector from the z-axis. So this in this figure you can see this is a cylinder, and the rho vector is actually directed radially outward from the z vector. So this is rho, and the phi vector actually corresponds to the direction of this point, or the angle of this point, or the angle of this rho vector with x-axis. So that is actually the second vector phi, second component phi, and the third is the z. So z in a cylindrical coordinate system is the same as the z-axis in Cartesian coordinate system. And here phi corresponds to the azimuth angle around the z-axis along the circular surface. So if we have the point over here, then phi will be tangent to the point at this tangent to the point is the direction of this phi vector, and its magnitude is actually calculated by measuring the angle between x-axis and the rho vector. So I will show you how to calculate the magnitude of this phi. So the z-axis along the z-axis is the same as Cartesian axis. So it is directed along the length of the cylinder. So this is a cylinder. So the length of the cylinder is actually aligned with the z-axis. So rho, phi, and z are perpendicular to each other, as is the case with Cartesian coordinate system and in spherical coordinate system as well. So all three components in one coordinate system are always perpendicular to each other. And if we want to transform the Cartesian components into spherical components, we can use these formulations. So x square plus y square root is equal to the rho vector. Phi vector is equal to tangent inverse y over x, and z vector is equal to z. They are same. So if we see the top view of this figure, so from the top we will just see a circle, so like this. So from the top we will just see the circle, and we will see these x-axis and y-axis. So from the top we will see such a view, and this is x-axis, this is y-axis. So this is our rho vector, as I have told you, and the angle of this rho vector with x-axis is phi, and the direction of phi is tangent to the point. So this is a phi, or this is the direction of a phi component, and this is the rho vector. So we can transform this rho vector into two components. This is horizontal component, this is called x. This is vertical component, and it is called y. So clearly x is equal to rho cos phi, and y is equal to rho sin phi, and z is equal to z. So this is how cylindrical components can be transformed to the Cartesian components. Similarly, this rho is equal to x square plus y square under root, and similarly this phi is equal to tangent inverse y over x, and z is equal to z. So this is how two coordinate systems can be transformed into one another. And now phi interpretation in four quadrants. If our point is lying in the first quadrant, then we will calculate phi using this expression. So phi is equal to tangent inverse y over x if the point is lying in the first quadrant, and in the first quadrant we will see that both x and y components are positive. If our point is lying in the second quadrant, then x will be negative and its y component will be positive, and in that case the phi will be calculated by phi minus tangent inverse y over x, because tangent inverse y over x will give us this angle. Okay, so this angle will be given by tangent inverse y over x, and phi is actually the angle between this rho vector and this x-axis. So this phi will be calculated by subtracting this tangent inverse y over x from pi. So this whole angle is pi, and if we subtract this angle, we will get this phi. So for second quadrant, this expression will be used. If our point is lying in the third quadrant, first we will calculate tangent inverse y over x, and that will be this angle, and we will add pi in this case. So this is the interpretation in the third quadrant, and in the fourth quadrant, this angle is phi, and a tangent inverse y over x will give us this angle, and after subtracting this angle from 2 pi, we will get this angle phi. So it is actually 2 pi minus tangent inverse y over x. But since we know that 2 pi corresponds to 0, so if we assume 2 pi equal to 0, we will get phi equal to minus tangent inverse y over x. And this dotted angle which is shown in these figures is actually equal to tangent inverse y over x. So this is how we can calculate phi if our point is lying in any of the four quadrants. Now, in cylindrical coordinate system, our vector will be given as a rho plus a phi plus a z. So these are the three components. If we want to calculate the component of a along rho, we will take the dot product of a vector with a rho. Okay, so all these dot products will become zero, and we will get a rho. Similarly, a phi is equal to a dot a phi, a z is equal to a dot a z. And if we want to transform one vector from cylindrical coordinate system to Cartesian coordinate system, we will have to calculate the dot product of the unit vectors. So first of all, ax dot a rho will be calculated, and since the magnitude of these unit vectors is equal to 1, so we will just get the trigonometric identity at the end, because in dot product a dot b is equal to ab cos theta. So the magnitude of this unit vector is equal to 1, magnitude of this unit vector is equal to 1. So we will only get the cos and some angle. So ax dot a rho can be calculated by drawing these two unit vectors. This is ax, this is a rho. The angle between them is phi, and their dot product will be equal to cos phi. Similarly, ay dot a rho. So this is ay, this is a rho. So it will be equal to cosine 90 minus phi. So cos 90 minus phi is equal to sine phi. Okay, so this angle will be used, and this angle is equal to 90 minus phi. And az dot a rho will be calculated, and it will be equal to 0, because z and rho are the components of the same coordinate system. So they are perpendicular to each other, and their dot product will be equal to 0. Now we will calculate ax dot a phi, and ax dot a phi uh, is equal to, this is ax and this is a phi. So a phi can be drawn over here, and this angle is phi, and a rho and a phi are perpendicular to each other. So the angle between a phi and ax will be equal to 90 plus phi. So it will be equal to minus sine phi. Similarly, ay dot a phi, this is ay, this is a phi. So the angle between them is phi, and it is equal to cos phi. And az dot a phi will be equal to 0. Similarly, az dot ax will be equal to 0. Az dot ay will also be equal to 0, and az dot az will be equal to 1. So in summary, we can write down the dot product of all the unit vectors with each other, and they can be represented in the form of tables. So in this example, we have to transform this vector field in a Cartesian coordinate system to the cylindrical coordinate system. So first we will calculate b rho, and b rho will be equal to b dot a rho, and it will be equal to y ax dot a rho minus x a y dot a rho plus z a z dot a rho. So ax dot a rho equal to cos phi minus x a y dot a rho equal to sin phi, and az dot a rho equal to 0. Now y is equal to rho sin phi, x is equal to rho cos phi. So it will become rho sin phi cos phi minus rho cos phi sin phi, and it will be equal to 0. So b rho is equal to 0. Now calculate b phi. B phi is equal to b dot a phi, and this is our b, and it will become y ax dot a phi minus x a y dot a phi plus z a z dot a phi. So putting the values of these dot products, we will at the end we will get minus rho sin square phi minus rho cos square phi. So minus rho can be taken as common, and we will get sin square phi plus cos square phi, and it is equal to minus rho. Similarly, bz is equal to b dot az, and it is equal to the same value, which is zaz. So bz is equal to z. So the overall vector in cylindrical coordinate system will be equal to minus rho a phi plus zaz. In the second example, we have to calculate the Cartesian components of this point. So this point is represented in cylindrical components. So here we have to calculate x, y, and z. X is equal to rho cos phi. So it is equal to minus 1.86. This is rho, this is phi, this is z. Similarly, y is equal to rho sin phi, and z is equal to 2. And now we have to transform this point in Cartesian coordinate system to the cylindrical coordinates. So here we have to calculate rho phi and z. Rho equal to x square plus y square under root, it is equal to 4.05. Phi is equal to So this point is lying in the second quadrant. So phi will be equal to pi minus tangent inverse y over x. So it is equal to 140 degree and z is equal to minus 3. In this last example, we have to transform this vector field to Cartesian components at this point 5 2 minus 1. So first we will calculate hx. Hx is equal to h dot ax. So it will be 20 a rho dot ax minus 10 a phi dot ax. So az dot ax will be equal to 0. So a rho dot ax is equal to cos phi, a phi dot ax is equal to sin phi, and phi will be calculated from this point, and it is equal to tangent inverse 2 by 5 because this point is lying in the first quadrant. Both x and y are positive, and it is equal to 21.8 degree. By putting this value in this cos phi and sin phi term, we will get 22.3. Similarly, hy is equal to 20 a rho dot ay minus 10 a phi dot ay. So this is sin phi and minus 10 cos phi, and it is equal to minus 1.85, and hz will be equal to 3. So now I am going to discuss differential volume element for a cylindrical coordinate system. So in cylindrical coordinate system, any point can be represented over the surface of a cylinder, and the differential volume element is basically a broken piece of a cylinder, and it is a small piece which is having the same dimensions and the same symmetry as that of a cylinder, complete cylinder. But this is a small piece or a broken piece of a cylinder. So in this broken piece or in this differential volume element, there are six surfaces, and the six surfaces can be seen in this figure. Okay, so this is the right surface, this is the left surface, this is the top surface, this is the bottom surface, and this is the inner surface, and that is the outer surface which is actually at the back side. Now we have to calculate the surface area of each surface. So there are actually total six surfaces, and the surface area of each differential surface can be calculated using the formula which we have just discussed. Okay, so now this is the right surface, and on this surface the angle phi is constant, and d rho is actually the length of the differential element along the rho axis, and this is the z axis, and the differential length of this edge is equal to dz. So the surface area of this surface will be equal to d rho multiplied by dz, and this is also called phi is equal to constant plane. Similarly, the left surface, which is actually not visible from this view, and it is actually this surface, and for this surface phi will be equal to phi 2, and again its differential area will be d rho multiplied by dz. So this is right surface and this is left surface. Similarly, we have a top surface, and the differential area of this top surface is rho d phi multiplied by d rho, and similarly for the bottom surface the differential surface area is equal to rho d phi multiplied by d rho, and z will be constant for the top surface and the bottom surface, and z will be equal to z1 for the bottom surface, and z will be equal to z2 for the top surface. And now the two surfaces left are the inner surface and the outer surface. For the inner surface, the differential area will be equal to rho d phi multiplied by dz, and rho will be equal to rho 1 for this inner surface, and the surface area of the outer surface will be rho d phi multiplied by dz, and rho will be equal to rho 2 for the outer surface. Because these two surfaces, the inner surface and the outer surfaces, these are actually curved in nature. So one length will be straightforward dz, the length which is going in the vertical direction, that is dz, and the length of this curved edge will be equal to rho d phi. So this is a curved edge, and it is also called as arc. So we know that the length of the arc s is equal to r theta. This is a common expression for the arc length, and the length of this arc will be equal to rho d phi. So the total area will be rho d phi multiplied by dz, and similarly for this it will be rho d phi multiplied by dz. But for the inner surface, rho will be equal to rho 1, and for the inner surface rho 1 will be smaller. For the outer surface, rho 2 will be greater than rho 1, and clearly the area of the outer surface is also greater than the area of the inner surface. If it is understandable to you, then the rest of the discussion will be very simple. So for the inner surface, rho will be constant and it will be equal to rho 1. The area will be equal to rho d phi dz, and for the outer surface, rho will be constant and it will be equal to rho 2, and the differential area will be rho d phi dz. So it will be rho 2, and here we will have rho 1. So for the top surface, z is equal to constant plane. For the right surface, phi is equal to constant plane, and for this inner surface, rho is equal to constant plane. So for each surface, one coordinate of the cylindrical system will be constant, and the differential volume of this entire piece, the differential piece, will be equal to the product of all the three differential lengths. So d rho d phi multiplied by dz. So the product of all these differential lengths will be giving us the differential volume of the piece, cylindrical piece. So when we want to calculate the total volume of the differential volume element, we will just integrate along all the three axes and it will give us the total volume of the cylinder or the differential volume element. Similarly, we can calculate the surface area of each of the six surfaces, and we can also calculate the length of each of the edge if we know these definitions of the differential lengths. So now we will solve a very comprehensive example, and upon completion of this example, all the concepts related to the differential volume element of a cylinder will be clear. So in this example, we are given rho variation of rho from 3 to 5, variation of phi from 100 degrees to 130 degrees, and variation of z from 3 to 4.5. So in this differential volume element, the row is varying from 3 to 5. So the here row is 3 and here row is 5. Similarly, z is varying from 3 to 4.5. So for the lower surface, z is equal to 3. For the upper surface, z is equal to 4.5. And phi is actually varying from 100 degrees to 130 degrees. So here phi will be equal to 100 degree and here phi will be equal to 130 degrees. So first of all, we will have to calculate the total volume of this element, and we will use the expression for the differential volume, which is rho d phi dz, and we will integrate all these three variables in the given limits. So by putting the limits of this rho, this phi and z, we can easily calculate the total volume. So first we will calculate the integration with respect to rho d rho. So it will be rho square by 2. By putting these limits, we will get 8. Similarly, d phi, the integral of d phi will be equal to phi, and we will put 130 minus 100, so it will be 30 degrees, and then that 30 degrees must be converted to the radians by multiplying it by pi by 180. Similarly, dz has an integral of z, and it will be equal to 4.5 minus 3, and it will be equal to 1.5. So overall, the total volume of this piece is 6.28. Now we will calculate total area of all the six surfaces. So we have six surfaces: right, left, top, bottom, and inner and outer. For the right surface, phi is constant, so differential area will be equal to d rho dz, and we can put these limits. For the left surface, again, this expression will be used, and these limits will be used for d rho and dz. For the top surface, we will have this differential area rho d phi, and we can easily put the limits of rho and d phi, rho and phi, and here again we will put the limits of rho and phi. So this is again a double integral which is called a surface integral, and finally we will calculate the area of the inner and the outer surfaces. The differential area for the inner surface is rho d phi dz, and rho is equal to 3, and for the outer surface the differential area will be equal to rho d phi dz, and the rho will be equal to 5 for the outer surface. So these are all simple integrations. We can perform these integrations, and then we can substitute all the required limits, and at the end we will get the answer of 20.67, and this is the total surface area of all the six surfaces. Now in the third part, we will have to calculate the total length of all the 12 edges. So here we have 12 edges. So this is the first edge, this is the second edge, this is the third edge, and there will be the fourth edge which is not visible. So there are four edges along the z-axis. Similarly, there are four edges along the rho axis. So this is rho axis, this is second, this is third, and there will be the fourth one. Similarly, there are four edges along the phi axis. So this is phi, this is one, this is two, This is 3, and here will be the fourth edge along the 5. So we can easily calculate the length of all the 12 edges. So first of all, just calculate the edge along the z-axis. So there are 4 edges, and z is varying from 3 to 4.5. So 4 into dz, and after that integration, we will get the answer of 6. Similarly, along d row, the along the row axis, the limits are 3 to 5 for the row vector, and there will be 4 edges. So we can have the value of 8 for the 4 edges along the row vector. For the edges along the 5 vector, there are actually again 4 edges, but these inner 2 edges will have smaller length, and these outer 2 edges will have the greater length, because the value of row is 3 for the inner edge and 5 for the outer edge. So for the row is equal to 3, we will calculate the total length of the two edges, and it will be equal to 3.14, and for the outer two edges, rho will be put as 5, and after putting these limits and converting the angle into radians, we will get this answer, and after adding all these edges lengths, we will get the total answer of 22.37. Finally, we will have to calculate the length of longest straight line within the volume, and it will be between points P3 134.5 and Q 500 degree and 3. So the longest length of the straight line will be actually the line from either this point to this point, right? So if we take the example of a room, then in the room, if we draw a diagonal from one corner to the other corner, one corner at the top and other corner at the bottom, and that straight line or that diagonal must be going through the center of the room, then that will actually be the longest length of the line. So here in this case, if we draw a straight line from this point up to this point, so this is the outer surface, and the top corner, this is the inner surface, and the bottom corner. So that straight line will have the maximum length. Similarly, we can also calculate the length of a straight line from this corner up to this corner. So that straight line will also have the same length as for the previous case. Similarly, that longer straight line can also be drawn from this point up to this point. So that will also be the longest length, and all these longest lengths will be equal. So in this example, I have actually considered this point and this point, and if we identify these 2 points in cylindrical coordinate system, we just have to transform these points to the Cartesian coordinates, and then we will have to apply the distance formula between these 2 points. So for this point, rho is equal to 3, phi is equal to 130 degree, and z is equal to 4.5, and for this point, rho is equal to 5, phi is equal to 100 degrees, and z is equal to 3. So these are the 2 points. So 3, 130, 4.5, and 503. So let's convert these 2 points to Cartesian components. So for P, we will have x is equal to 3 cos 130 degrees, because x is equal to rho cos phi, y is equal to rho sin phi, and z is equal to 4.5. And for this point, x is equal to 5 cos 100, y is equal to 5 sin 100, and z is equal to 3. So these are the coordinates of P, and these are the coordinates of Q. Now just apply the distance formula between these 2 points by taking the squares and then add the answers and then take the square root. So it will be equal to 3.2. So that is the length of the longest straight line from one point to the other. So hopefully that lecture is quite understandable to you. And for watching more videos, please subscribe to this channel. Until the next lecture, it's goodbye.